This section is nominally about taking a random variable x and calculating a new expected value, the conditional expected value of x given an event b. And as you can imagine, we'll do this using the conditional PMF given b or conditional PDF given b. But more generally, this section is about the fact that once you condition on b, a random variable x becomes a new random variable x given b, and it has all of the usual properties of a random variable. In particular, we think of the PMF of x given b as a new PMF for a random variable x given b, and this PMF is always greater than or equal to 0. It sums to 1 over all possible values, but in this case, the set of all possible values is b because we've conditioned on x belonging to b. And finally, for some other event c, we can calculate the conditional probability of c given b by simply summing this new PDF over all possible elements in the set C. And of course, we have exactly the same analogous set of results in the continuous case. We have a conditional PDF that's always non-negative. Over the set B, this conditional PDF has to integrate to 1. And the probability that x is in a set C, i.e. the conditional probability of C given B, is the integral of this new conditional PDF over the set C. Essentially, these are the same definitions we had before, but we've just replaced the PDF of x with the PDF of x given B. With these conditional distributions, we get corresponding conditional expected values. So when x is discrete and is described by the conditional PMF of x given b, we sum that weighted by the values of x, and we get the conditional expected value of x given b. Similarly, in the continuous case, we get the conditional expected value of x given b by integrating x and its conditional PDF over all possible x. We could have written this integral as being over the set B, but in fact, because this PDF, this conditional PDF, is 0 outside of the set B, we can just write it in the usual way as being over all possible values of x. When x is described by a bunch of conditional distributions in different modes bi, we can now calculate expected values for each of them and then combine them by weighting by the probabilities of those different modes. This theorem is just a simple consequence of how we synthesized the PDF of x from the conditional PDF of x given the bi's. Specifically, we recall that we found the PDF of x is the sum over I is 1 to m, f of x given bi of x times b of bi. And now expected value of x is the integral of x times the PDF of x. And this becomes the integral of x times dx. And now we take this one integral and write it as a sum of m integrals. And when we do this, we obtain summation I equals 1 to m integral x times the conditional PDF of x given bi times bi times dx. When we bring the p of bi outside the integral, we're left with x times the conditional PDF of x and dx. And the result is our final theorem. Here on this slide, we see the same proof in the discrete case, and the logic is exactly the same. The key, of course, is that in the discrete case, we have broken up this PMF of x, right, into a sum of conditional PMFs weighted by the probability of the different modes. These ideas, of course, generalize to the case of functions of a random variable x. In this case, we have some condition b, and we're interested in the expected value of g of x given the condition b. Just as we did in the unconditional case, we simply average the function by over the distribution. And in this case, the distribution is either a conditional PMF of x given b or a conditional PDF of x given b. So, for example, if g of x is equal to x squared, then we get the conditional second moment of x given b, and the continuous case would be x squared Of course, we're often interested in central moments, and in this case, it's helpful to define mu of x given b as another name for the expected value of x given b, and then you might be interested in also calculating a conditional variance of x given b, and the conditional variance of x given b is exactly as stated here in the theorem, but there's one thing to be careful about. It's that you have to use this conditional expected value here, mu of x given b. The key thing to remember is that once you say, oh, we're conditioning on event b, we're calculating a conditional variance, then you have to do all of your averaging, your expected values, using either the conditional PDF of x or the conditional PMF of x. If you remember the quiz from section 7.1, we had that y was a uniform 0-10 random variable, value 1/10, and we found that the probability y was less than or equal to 0.6. And from that we found that the conditional PMF of y given y was less than or equal to 6 was a uniform 0.6 PMF. So in fact, once you make that observation, the rest of this problem is really trivial. So the expected value of y, given y is less than or equal to 6, right, is simply the expected value of a uniform 0-6 random variable, which of course is 6 plus 0 over 2 equal to 3. It's the old a plus b over 2 formula for continuous uniform AB random variables. Similarly, the variance of y given y is less than or equal to 6, well, given y is less than or equal to 6, y is continuous uniform 0-6. That's what we see in this PDF. And so we can simply write down that this is 6 minus 0 squared over 12, or also equal to 3. If you paused in the middle of this lecture to work out the details of quiz 7.1a, the discrete quiz for section 7.1, then you would have derived the conditional PMF of n, given n is less than or equal to 10, and then these next two steps where you find the expected value and conditional variance are a little bit tedious, but not too tricky. You can check your answer on the next slide.